Hello and welcome back to another lecture from organic chemistry, and thank you very much for watching this lecture video. Now that we've finished nomenclature of carboxylic acid, it's time to maybe start reviewing some chemical and physical properties of carboxylic acid. Okay, so the molecule that we have, it has a functional group of COOH. Let's zoom on the electrophilic carbon of that functional group. So the carbon that I'm talking about it is this carbon. We have a carbon there with sp2 hybridization. And because it's a sp2 hybridization, I try and expect actually geometry to be trigonal planar. Trigonal or trigonal planar. Okay, that means the addition, it can happen from the bottom, from the top or the bottom of the molecule. And then if that's the case, then expect sometime, like when you're taking carboxylic acid and you transfer it to something else, you might get chiral on center. So keep this one in your mind. Now, we have oxygen electronegative element that is attached to the carbonyl group on one side, and the other side there is an H attached to oxygen. Anytime you have hydrogen attached to an electronegative atom like nitrogen, oxygen, fluorine, we say we have hydrogen bonding, or we can have hydrogen bonding. So now this hydrogen is going to have a huge positive charge because it's attached to oxygen, which is a electronegative element, and that's going to pull good electron density from it. Hydrogen is short of electron density. It will look for that electron density, and it will find it in the oxygen atom of the carbonyl group. And because that carbonyl group, it has two lone pair, and it can actually share the lone pair with hydrogen, and in order to reduce the partial positive charge on it. And the interaction between hydrogen and oxygen that I'm going to highlight, this oxygen, and we call it hydrogen bonding. Hydrogen bonding. Hydrogen bonding is going to have a dramatical effect on technically structure of the molecule, and also the boiling temperature or physical property of the molecule. And so the boiling temperature is going to go up because we have intermolecular forces between the molecules. And in order to evaporate the molecule, we need to chop those actual intermolecular forces. If you take a carboxylic group and put it in a protein and now talk about the physical or chemical properties there, I can say because we do have hydrogen bonding, we can have hydrogen bonding, and the proteins always will be surrounded or they will be in aqueous media. So expect to have hydrogen bonding between those carboxylic acid or the protein and or another sheet from like another protein. And that means they're going to affect the shape of the protein. And now, anything that gets rid of those interactions, it will affect the shape of the protein and the solubility. For example, solubility or some of the physical properties of that molecule will change maybe forever. One example: take milk. We know milk has fat, and if you take milk and you heat it, very soon you will have a fine layer of fat sitting on the top. It doesn't matter really how much you mix it. Like if you let it cool and you try to mix it, and it doesn't matter how much time you spend, that fat is not going to get back inside the milk because you changed the geometry. You got rid of some of those intermolecular forces, including the hydrogen bonding of the carboxylic group. Now, carboxylic group it has acidic hydrogen, so that means it can react with a base, and a strong base like sodium hydroxide. It will take that H and it will leave us with the carboxylate. Okay, carboxylate. When you say ATE, you're talking about a negative charge, a species with a negative charge, a species that has oxygen. It has more than one oxygen, and now there is a negative charge there. And so that's going to be technically the conjugate base of the carboxylic acid. So whenever we are talking about the conjugate base of the carboxylic acid, we will replace technically the OIC like acid by OAT, and in this case, for example, benzoic acid, it will be replaced by sodium benzoate. And so as I said, like we have OIC, and I'm going to replace the IC and acid. I will replace the entire of this one by ATE. Okay, in water, because you are dealing with acid, that acid it can exchange a protein with water, and it depends to the pK of the acid. The reaction might go completely to the right side, or no, maybe you will have equilibrium, and it depends to the pKa. Like the way you will show those equilibrium is going to be different. So, for example, in this case, as you see, the bigger arrow is pointing to the reactant side. What does it mean? It means the carboxylic acid is not that strong acid. When it's reacting with water, yes, it's giving protein to water, and it's turning to technically the acetate plus hydronium ion. But we were going to have plenty from unreacted acid at the end. So the equilibrium is going to have plenty from this molecule. Now, if you play with, play with this substituent that attach to the carbonyl group, you can actually change the position of this equilibrium. When I say playing with those substituents, remember, we are getting a negative charge, and that negative charge is not going to be that stable. We need to stabilize it. If you put any with electron withdrawing group here, they can pull the electron density from oxygen, and that's going to stabilize the acetate or the anion, the conjugate base. It will shift the reaction to the right side. And let's review them. We have pKa, for example, for benzoic acid is a 4.19, and now if you replace it by methyl, it's like 4.76, and if you replace it by ethyl, it's 4.87. Ethyl and methyl are not that different, but the one that I wanted to talk about it is why the benzoic acid is that far. It's way different. I know that this group is electron withdrawing group. The more we have from it, the higher acid we get. Remember, higher, if we say if pKa goes up, that means we get weaker acid. Okay, so from left to the right, the pKa is going up. That means this is going to be stronger. Benzoic acid is stronger than this acid, acetic acid, and then the last one. What's the reason behind it? I have electron withdrawing group or a phenyl ring, and then I replace it by CH3. This is CH3. This is electron donating group. So I switch it from electron withdrawing to electron donating group. Then I added one more carbon, and I know ethyl is more electron donating than methyl. So this time I'm gonna pour electron density inside the carbonyl group. That means the force, the hydrogen atom, this hydrogen atom that I'm gonna highlight, the force that hydrogen atom is going to feel from the carbonyl or from oxygen, it will be less. And if it's less, you will be dealing with a weaker acid. Now, compared to hydrochloric acid or sulfuric acid, carboxylic acid are really, really weak. Why? Because their pKa are hanging around 4 to 5, while HCl, it has a pKa around -7, I think. So pKa of 5 versus -5 is way different. That means you can easily say they are really, really weak compared to sulfuric acid or hydrochloric acid. But if you take them, and compare them, for example, with ethanol, and then you'll see dramatical, difference between them is around 10. The gap between them is around 10. So I'm going to say the acetic acid is way, way stronger than ethanol molecule. And the reason for it, whenever we take H from ethanol, we will get this species with -1 charge that does not have any resonance structure. But if I take H from acetic acid, that's going to leave me with acetate that it has 2 resonance structures. And the more resonance structure you have, the higher stability the conjugate base will get. So the conjugate base will be more stable whenever you're talking about acetic acid. And because it's more stable, the reaction is going to shift to the right side. That means it will wants to actually release H+. So the acid will be stronger acid.